Hello, this is Lecture 6b for ECE 361, Probability for Engineers, Fall 2016. In today's lecture, we'll cover three topics. First, Section 3.3 on Gaussian or normal random variables. Second, Section 3.4 on joint probability density functions for multiple random variables. And third, Section 3.5 on conditioning, which we will start but not finish in today's lecture. Let's start with our first big topic on the Gaussian distribution. The Gaussian distribution, or normal distribution, is a continuous distribution that has as its support the real line, as indicated here. Its PDF at little f sub x is given by this expression here. You see that it's an exponential where the argument of the exponent is squared in x. As you can see, this distribution has two free parameters, mu, which can take any value in the real line, and sigma, which can take any non-negative value in the real line. And these two parameters dictate the shape and characteristics of the corresponding distribution. First, let's discuss mu, which is the mean. We will show in a few slides that if I generate a Gaussian random variable with parameter mu, that random variable capital X has expectation equal to mu. And we will see further that changing mu shifts the PDF so that it's centered at mu. The standard value of mu is going to be 0, meaning that the PDF is centered along the y-axis. The second parameter is sigma. And we will show in a few slides that if I generate a Gaussian random variable with parameter sigma, then it will have variance sigma squared. And consistent with what we've talked about in the past about variance, changing sigma scales the PDF, either stretching it for sigma larger than 1 or compressing it for sigma positive but less than 1. The standard value for sigma is 1, which means that the variance of a standard normal random variable is unity. In terms of notation, our notation is fairly standard. We will write x as a capital letter to indicate that it's a random variable. The tilde symbol again means to be read as is distributed as. The capital N now stands for normal, and then the two parameters mu and sigma stand for the two parameters of the distribution. I'll hasten to emphasize that it is often also common for some authors to write that the second argument stands for sigma squared. To understand the distinction, suppose I was to write x is distributed normal with parameters 0 and 2. If this is the understood convention, then we know that sigma is 2 and sigma squared is 4. If instead this is the understood convention, then sigma squared equals to 2 would correspond to sigma equal to root 2. So please pay attention to that, and please recall that our notation will be for sigma to be the argument in the second position. I mentioned the standard values for mu and sigma on the previous slide, and as we'll see, the standard Gaussian normal plays an important role in understanding the behavior of the general normal. And as is also convention, we will use the capital letter Z to indicate a standard normal. So again, a standard normal is 1 with parameters mu equal to 0, centered at the y-axis, and sigma equal to 1, meaning the variance is equal to 1. And so, consistent with our notation, if I write Z tilde n01, it's to be understood to mean that Z is a normally distributed random variable with parameters mu equal to 0 and sigma equal to 1. So this expression here results simply by setting mu equal to 0 and sigma equal to 1 in the previous expression. Here's a picture of the so-called famous bell curve, which is the probability density function for a standard normal. And what you see here is the x-axis has been drawn from range -5 to +5, and that encompasses most of the mass underneath the curve. I have vertical grid lines here at 0 and ±2, which corresponds to plus or minus 1 and 2 standard deviations respectively. So you'll see since mu equals 0 that the distribution is centered at 0. Now consider what happens when I set mu equal to 2.5. You see how the distribution shifts so that it's now centered at mu equals 2.5. I've again drawn those grid lines at plus or minus 2 sigma and plus or minus sigma, which now correspond to 2.5, 1.5, and 0.5, as well as 3.5 and 4.5. The only effect, however, of changing mu has been to shift. It has not been to scale. So now what we're going to do is consider the case where mu equals 0, but sigma equals 2. And that's drawn here. And now you see that the distribution has been stretched out in accordance with the fact that sigma equals 2 is going to have a variance of 4 times as large as the variance of 1 for the standard normal. And now my grid lines at plus or minus sigma and plus or minus 2 sigma are positioned at -4, -2, +2, and +4. So hopefully that gives you some graphical understanding of the impact of the two parameters mu and sigma on the shape of the Gaussian probability density function. So let's now get into some of the mechanics. We know that in order for a function to be a valid probability density function, it must have two key properties. First, it must be non-negative, and second, when you integrate that PDF over its support, that integral must equal 1. Now, the non-negativity of the given normal PDF is obvious from the definition. The exponential function is never negative. The fact that the Gaussian distribution does integrate to 1 is not obvious and is in fact a little bit difficult to show. The correct statement here is that if we integrate the probability density function for the normal distribution over the entire real line, where in this equality here I've substituted in that PDF and pulled out the constant which is independent of x, that this integral does in fact equal to 1. We're not showing that. I'm asking you to take that as true without proof. Recall some of our discussion from the last few lectures on the relationships between the probability density function, little f sub x, and its corresponding cumulative distribution function, capital F sub x. In general, not just for the normal distribution, but in general for a continuous distribution, we know that we can always express the CDF, capital F sub x, in terms of the PDF, little f sub x, by integrating the PDF over all values from -infinity up to x, where x here equals the argument of the CDF. Again, recall the interpretation that capital F sub x, the CDF, stands for the probability that the random variable x takes a value less than or equal to little x. Now, in what we've done in the past, we've been able to then, given this integral, substitute in the form of the PDF and then evaluate the integral, getting an explicit expression for the CDF of the distribution. Now, there's no guarantee that that will always happen, and in fact, with the normal distribution, it does not. So, using this general rule up here, substituting in the form of the normal PDF, I get this expression here for the CDF, and you might then ask, well, what then does this integral evaluate to? And so the point here is to say, it is not easy to see this, but it can in fact be shown that there is no solution to this integral that provides an explicit algebraic expression for the standard normal distribution, or sorry, not the standard normal, the arbitrary normal distribution in terms of the arguments x, sigma, and mu. That is, if you want to evaluate the normal CDF, you have to evaluate this integral numerically. So as it says here, the CDF for the normal distribution is only expressible as an integral of the PDF. The normal CDF must be found by a computer or through tables, and we'll go through both of those. Now, one of the key properties, which is immediately obvious if you've looked at this curve, is that it has a symmetry. There's a symmetry around the value mu. So here I've drawn a normal PDF, and with mu equal to some positive value, I think I chose mu equals 2.5. And you can see that if I chose any value x, and I happen to choose here x greater than mu, that the height of the density at x equals the height at the density at this value 2 mu minus x. And the point 2 mu minus x is distinguished as having the same distance from mu, namely x minus mu, as is the distance from x to mu. Both these intervals have length x minus mu. Okay, and so that's obvious graphically that this is the right point that has to find to demonstrate the symmetry of this distribution, but it's also easy to see immediately from the definition of the PDF. So let's evaluate the density of the normal random variable x at the point 2 mu minus x. So what I do is, this is my argument, and I substitute it in as the value for x. Now, up in this exponent, I see I have the quantity 2 mu minus x minus mu quantity squared. And so 2 mu minus x minus mu is the same as mu minus x squared. And, of course, that's the same as x minus mu squared. But now what I have, of course, is recovered the original PDF at x. So thus, the density of the normal random variable at 2 mu minus x equals the density of the random variable x at little x. So those are two ways, a graphical and an algebraic way of seeing the symmetry of the distribution. And that symmetry can be leveraged, as we will see. In particular, any distribution, not just the normal, any distribution that has that property of being symmetric about some number mu has the following two properties. First, that value mu must be the median of the distribution. Now, we haven't talked about the definition of the median, but many of you will have known that word from everyday life. And the median of a distribution is that value for which half the probability is above and half the probability is below. That is, you choose the value, the median, m, say, has the property, the probability that the random variable x is above the median is equal to the probability that x is below the median, both of which are equal to 1/2. The second property is that value mu must also be the mean. Note that in general there's no necessity that the median and the mean have equal value. The mean is the weighted sum of the values, weighted by the probabilities of taking those values, and the median has this property that half the mass is below and half the mass is above. They will coincide, however, for these symmetric distributions like the Gaussian. So what we're going to do now is we're going to use the fact that we have a symmetric distribution to prove these two properties. And to emphasize, this proof has nothing particular about the Gaussian distribution. We're only going to use the fact that we have a continuous distribution that's symmetric around mu. So let's first prove the median property. So we know that if we integrate the density over the entire real line from negative infinity up to positive infinity, we're going to get 1. So that's our starting point. 1 equals the integral from negative infinity to positive infinity of the PDF over x. Now what we've done here in this first step is we've split that integral at this value mu, and just express that single integral as a sum of two integrals over disjoint intervals. Now, in the second step, we've done two things. First, because the PDF is symmetric around x, around mu, I know that f sub x at little x is equal to f sub x at 2 mu minus x. So I can always make that substitution. In the second integral, corresponding to this one up here, I recognize this is the integral from mu up to infinity of the PDF over all x. And that corresponds to simply the probability of the event that the random variable x is larger than mu. Now, in the third step, what I've done here is I've done a change of variable, and I've used the variable y equal to 2 mu minus x. And making that change of variable has the effect of flipping around the order of integration, and it's then now easy to see that again I have the same integral I had before, just with a different dummy variable y now instead of x. But again, this is the probability that the random variable x is larger than the value mu. And so therefore I have that 1 equals 2 times the probability that x is greater than mu. Or of course, that's the same as saying the probability that x is greater than mu equals 1/2, which is the defining characteristic of the median. Next, we're going to show the second property, that if I have a distribution that is symmetric around some number mu, then that number mu must be the mean of the distribution. And the proof is very similar. In particular, we're going to again split the integral and use a change of variable. So now I know from definition that for any continuous random variable, if I want to find its expectation, I integrate the PDF f sub x times x over all possible x from negative infinity to positive infinity. And that will equal, by definition, expected value of x. So in this first step, all I'm doing is I'm splitting the integral at mu and adding up the two parts. And now what I do with this first integral in the second step is I use the change of variable x equal to 2 mu minus y, and I use the symmetry property so that when I substitute 2 mu minus y here, it's the same as y. In the second integral, I leave that one as it is. Now in the third step, what I'm doing is I'm splitting this integral here. This difference here is going to give me two integrals, plus this one is going to give me a third. Now this first integral is going to be 2 mu times integral from mu to infinity of f sub x of y dy. And then I'm going to subtract out the integral from mu to infinity of y f sub x of y dy. That's the exact same as this integral, which is to say that the second integral and the third integral cancel with each other, leaving only the first, this one down here. And again, this integral of the PDF over all y now from mu to infinity is simply the probability that x is greater than mu. And so what I have shown then is that e of x equals 2 mu probability x greater than mu. But from the previous exercise, we know that probability x greater than mu is equal to 1/2. So this equals mu. Thus, in conclusion, the expected value of this random variable must equal mu, the point at which the distribution is symmetric. Okay, so that verifies for us that this parameter mu corresponds to the mean and in fact also the median. Let's move on now to interpret the second parameter of the distribution, sigma, and in fact we want to show that sigma squared is going to be the variance of a normal distribution. Now, the definition of variance for any distribution, not just the normal, is that we say that the variance of the random variable x is the expectation of the following function of x, namely the function where I take x, subtract out its mean, and square it. So we call this the mean squared error. It's the mean or expected value squared error, x minus mu, or deviation of x around its mean. And by definition of expectation of a function of a random variable, that this expression here is equal to this integral here. Okay, so now all I'm going to do is I'm going to substitute in the particular form of the normal PDF in right here. And that's what I'm doing down here. I'm saying the variance of a normal random variable x is given by this general expression where I've put in the PDF for the normal and I've pulled out the constant, which does not depend upon x. And now what I'm going to do is do a change of variable formula, y equal to the ratio of x minus mu over sigma. Now, as we'll see in a little bit, this particular change of variable, you'll first see that it's a linear change of variable. It's a linear function of x with slope 1 over sigma and intercept negative mu over sigma. And second, it has the property, as we will see, that this change of variable, if we think of y as a random variable and x as a random variable, that this random variable has mean 0 and variance 1. So this can be thought of as the standardization operator, as we will see soon. For right now, though, it's just a simple change of variable. So I have here the quantity x minus mu squared. I put in y squared, and I compute dx and dy. You see that the sigma will fall out. I won't go over all the details. And now I'm left with this integral here. You again have to use integration by parts, and I won't go over the details of that, but if you work it all out, you'll be left with this integral of the variance of x is equal to sigma squared. Okay, so now we know that when we say that x is normal with parameters mu and sigma, that mu corresponds to the mean and sigma corresponds to the standard deviation. Equivalently, sigma squared is the variance of that distribution. All right, so the Gaussian distribution is famous for many reasons, and we'll be talking about it as the course goes on. But one of the reasons it is rare and famous is it has this property that's called stability or closure, depending upon which term you like to use. And so let's to motivate that, let's observe the fact that we've already seen in talking about continuous random variables several different families of distributions. A family of distribution is simply a collection of distributions indexed by some parameter value. So it's nothing new. What we've seen already, for example, are three different families: the uniform, the exponential, and the normal. So, for example, the uniform family of distributions might be parameterized by values L and U. And so if I write x is distributed as uniform over the interval L and U are understood to be parameters of that family. So choosing different values of L and U gives you different members of the family. Likewise, we've introduced the exponential family of distributions indexed by its parameter lambda. So if I write x is distributed as exponential lambda, we understand that to be that x is an exponential random variable with that parameter, and different values of lambda will correspond to different distributions, both of which are in the same family. So the situation is no different for the normal. We talk about n mu sigma as the normal family of distributions indexed by the pair mu and sigma. Now, so that's all that I mean by a family of distributions. But now let's consider the following notion of combining different random variables from a given family. So I take two random variables from a given family, say the pair x and y. For example, suppose that x and y are each uniform over some interval c to d. And then I form the random variable ax plus by, or even just ignore a and b and just consider the random variable x plus y. Okay? In general, forming a linear combination of random variables, whether drawn from the same family, whether identically distributed or no, will lead to a new random variable that is not in that family. So here's two examples. If x and y are independent uniform random variables, say over the interval 0 to 1, then the distribution of the random variable x plus y is not uniform. In particular, it has the Irwin-Hall distribution, which we haven't talked about it. You can ignore it. The only point is that the Irwin-Hall is distinct from the uniform distribution. A second example, using our second family, exponential. If x and y are independent, say unit rate exponential random variables, then x plus y is not an exponential random variable. In particular, x plus y now has the gamma distribution. Again, we haven't talked about the gamma distribution, and I'm not asking you to learn about it. The only point is to understand that this linear combination of independent random variables has led to a new random variable which is not in the same family as x and y are from. So the point of this slide is really to say this, that most distribution families used in probability are not closed under linear combinations. Okay, that's what I mean by closure in this sense, is if I take two random variables from the same family, form a linear combination, that linear combination will not in general be in the same family. If it is, we say that the distribution is closed. So all this is leading up to the claim that the normal distribution, the family of distributions, is closed, again, also called stable. Again, what does this mean? It says if I take two normally distributed random variables and form a linear combination of them, I yield a new random variable which happens to also be normal. So in using symbols, suppose x is normal with parameters mu sub x and sigma sub x, and y is normal with parameters mu sub y and sigma sub y. Suppose x and y are independent. Then the linear combination ax plus by is also normal with some parameters mu sub z and sigma sub z. Again, we're not going to prove this fact. This is beyond the scope of the course, but it's important to understand that it's nonetheless true. And then the question might be, well, if you know that there are some parameters mu z and sigma z such that ax plus by is normal with those parameters, what would those parameters be? And that we can do, because all we need for that are the rules we've already learned. In particular, let's use linearity of expectation. We know that the expected value of a linear combination of random variables is the same linear combination evaluated at the expected values of the random variables involved. And so, jumping down here for a bit, the expected value of ax plus by, that is expected, which is going to equal mu sub z, is a times mu sub x plus b times mu sub y. And the second rule we require is, recall that if x and y are understood to be independent, then we can use the fact that the variance for a linear combination of random variables will equal a corresponding combination of the variances. I won't say linear combination because it depends upon a squared and b squared, but it's nonetheless easy to use this rule to find out what our parameter sigma sub z should be. In particular, the variance of ax plus by is going to be a squared times the variance of x plus b squared times the variance of y. And therefore, my parameter sigma z squared should equal this, and sigma z should equal the square root of that expression. Okay, let's talk a little bit more about the standard normal and how we actually compute it. So we've introduced this notion of the capital letter Z distributed as n01 to be understood as meaning that Z is a standard normal being shorthand for mu equal to 0 and sigma equal to 1, i.e. the mean is 0 and the variance is 1. And so here it is again the PDF for the standard normal and the CDF. Now again, recall that the CDF cannot be expressed in any explicit form. It can only be expressed exactly as an integral, this particular integral, and it cannot be simplified. And so we're going to use, as is standard and as our book uses, the notation capital phi of z. And capital phi of z means nothing more than the CDF of a standard normal evaluated at z. So it's just a new piece of notation. It's a standard notation you'll find everywhere. And phi of z is going to be what's going to have to be tabulated or computed from our computer program. All right, so we'll show you a table on the next slide of what the table of phi of z looks like. And the value of phi of z is also available from almost any computer program that you can imagine. In MATLAB, you use the command norm CDF at z. In Mathematica, you would use CDF of normal distribution 0, 1 at z. And if you like Python, you would first import SciPy stats and then use the command norm CDF at z. All of these are very easy to use. But let's first look at a table. So this is a table I got from this URL on the internet. And you see that it has a table format, and this is very easy to read. The columns correspond to, as you see, the ones digit and the tenths digit, and the columns, or the rows, correspond to the ones digit and the tenths digit, and the columns correspond to the hundredths digit. So in particular, at 0.000, the probability that a standard normal is less than or equal to that number is 0.5. As you would expect, if I look at 0.00, the probability that the random variable is less than that is exactly 1/2. 1/2 the mass lies left of 0. If I look at 1.00, I see that the value is 0.8413. So the probability that a normal random variable takes a value less than or equal to 1 is 84.13%. And going down to 2, for example, probably that a standard normal random variable takes a value less than or equal to 2 is 0.9772. And again, these are not exact, these are approximate to the 10,000ths place. So they're easy to find these tables, they're easy to use, but it's just as easy to use your computer. All right, so there's a slight problem, you might say, in that the table in the previous slide gave us the CDF for the standard normal, but what if you're not dealing with the standard normal? That is, it's fine if we want to know the probability that a standard normal takes a value less than some little z that we're interested in. But what if we had an arbitrary normal, x, with a non-standard parameters, mu not equal to 0 and or sigma not equal to 1? What do? We standardize. Remember, I mentioned this a few slides back when we looked at the change of variable x minus mu over sigma. Now, this is an operation that applies to any distribution, not just to the normal. And it's very simple to understand. We're going to do the following. For any random variable x, if x has an expectation e of x and a standard deviation std of x, then its standardized version, denoted here by y, is simply the linear function of x formed by taking x, subtracting out its mean, and dividing by its standard deviation. And we'll see below why that would be of interest. But for now, just understand that this is a linear function of x. Again, the slope is 1 over the standard deviation, and the intercept is negative of the ratio of the expectation over the standard deviation. So the motivation behind this particular definition here is that we claim that no matter what the distribution of x is, that this random variable y has a mean 0 and variance 1. And these two lines establish those two facts. Let's first look at the mean. The expected value of y, I just substitute in the expression for y in here, and now I have the expected value of this linear function of x. And by linearity of expectation, I can pull out that constant. That's not going to affect the expectation. And now in the numerator, I'm looking at the expectation of x minus its mean. Excuse me. But expected value of x minus e of x is equal to e of x minus e of x, which equals 0. Next, let's look at the variance of y. So I'm looking at the variance of the ratio x minus its mean over the standard deviation of x. And again, this is a linear function, and I know how to compute variances of linear functions of a random variable. First, I want to write this as x over standard deviation of x minus the constant e of x over standard deviation of x. We know that the variance of x plus a equals the variance of x for any a, because shifting the distribution along the x-axis has no effect on how spread out it is. And so therefore I can focus on this variance of x over the standard deviation of x. And we know that the variance of bx is equal to b squared times the variance of x. Now in this case, b is equal to the 1 over the standard deviation of x. So when I pull that out, I'm squaring it. And the square of the standard deviation is the variance. So I'm left with the ratio of the variance of x over the variance of x, in other words, 1. Again, emphasizing that this operation of standardization applies to any distribution, not just to the normal. Okay, so why did I introduce that? Because this is precisely the tool we need in order to be able to apply the definition of the standard normal distribution in computing the CDF for an arbitrary normal distribution. So now I have x, which is normally distributed with arbitrary parameters mu and sigma, and I want to evaluate the CDF of that distribution at some candidate value little x in the reals. So we proceed. The CDF at little x is, by definition, the probability that the random variable x is less than or equal to little x. And now I want to use the fact that if, and it's written down here, I'm using two facts. Let's jump down here to the bottom because we want to make sure you understand why these two things are true. These are the two properties I'm going to use in the next step, and they are the following. The event that any random variable is less than or equal to any value, little x, is the same as the event that that random variable minus a is less than or equal to that x minus a for any a. In particular, the event that the random variable x is less than 2 is equal to the event that the random variable x minus 1 is less than 2 minus 1. And that should be apparent to you as to why that's true. So that we might call that the shifting property of event equivalence, and this might be called the scaling property of event equivalence. Here, if a is any non-negative value, or strictly positive value, then the event that the random variable x is less than or equal to the value little x is equivalent to the event that x divided by a is less than or equal to little x divided by a. For a concrete example, if a is 2 and x is 4, the event that the random variable x is less than 4 is equivalent to x over 2 being less than 4 over 2. Okay, so if you grant those two properties as being true, then you see I could also combine them, and that's what I've done here. I've said that the event that the random variable x is less than the little value of x is equivalent to the event that x minus mu over sigma is less than little x minus mu over sigma. But now in this next line, I recognize that what I've done to x is to standardize it. I've taken a normally distributed random variable that had parameters mu and sigma, subtracted out the mean mu and divided by the standard deviation sigma, and I know that that's going to transform this to a normally distributed random variable with mean 0 and variance 1. So note I've used two key properties in going from here to here. First, I've used the fact that the normal distribution is closed or stable. When I form this linear scaling, I'm confident that this new linearly scaled version of x is also normal. Also, I'm using the standardization trick. I know that not only is it going to be normal, it's going to be normal with mean mu and sigma 1. And so now what I'm asking for is the probability that a standard normal z is less than x minus mu over sigma. And that's going to equal the CDF of the standard normal z at the argument x minus mu over sigma, or in our new notation, capital phi at x minus mu over sigma. So in summary, I started with an arbitrary normal x with parameters mu and sigma, and I wanted to evaluate the CDF at some arbitrary value little x. And I wanted to do that using only knowledge of the standard normal CDF. And this derivation says that if you want to evaluate the CDF of an arbitrary normal x at some value little x, you use the CDF for the standard normal, available either by table or on computer, but the argument you use is computed by first taking the value little x, subtracting out its mean, and dividing by sigma. Let's do an example. Let's suppose that x represents the annual snowfall in inches over a given season. All right, so we are given these parameters mu and sigma, where we see that mu equals 60 and sigma equals 20. In other words, the typical season has a mean of 60 inches and there's a standard deviation of 20 inches. So we want, and we're told then, that the amount of snowfall is normally distributed with those parameters. And the question is, find the probability that the snowfall will be at least x equals 80 inches or more. Now, in this case, since little x is 80 and mu equals 60 and sigma equals 20, we see that 80 minus 60 equals 20 divided by 20 equals 1. Okay? So what we're doing now is we're doing the same argument we had in general for this particular values. I want to know the probability that the annual snowfall, the random variable x, exceeds 80 inches. That's the probability that that random snowfall divided by minus its mean divided by standard deviation exceeds 80 minus 60 over 20. In other words, now I'm using y here to denote the standardized version. I maybe should have called it z, the standard normal. So anyway, y is a standard normal. This is the probability that capital Y, the standard normal, exceeds 1. Now, whenever I have the probability that capital Y is greater than 1, I know that's equivalent to 1 minus probability that capital Y is less than or equal to 1. And that's equivalent to the CDF of Y at 1. So now I would go to my table, and recall we looked up this value. In particular, we saw that phi of 1 was 0.8413. So in summary, the probability that the annual snowfall is more than 80 inches is 0.1587.